first of all, thanks to the organizers for organizing a finally in-person conference. I have to admit, to me, it's nice to just see any adults in person. But this is like extra nice. Yeah, my title on the website was a little bit broad. It just said radiation. But what I'll be talking about is so classical radiation at one loop. And it's based on work done with the people who are all here. So Saad, who's there, and Matteo, and don't know who's behind there. And I'll be talking about how we can extract these classical radiation observables from scattering amplitudes. Yeah, and here's the archive paper. There'll be a new and improved version, hopefully very soon. So luckily for me, there have been a lot of very good motivations for why we would want to look at the binary spiral problem. Wojtek gave a much better introduction yesterday, I think, than I could, and Ricardo also. But this is essentially the problem that we've been interested in, right? These two black holes or gravitating bodies that gravitate around each other and then emit some kind of radiation that we're interested in. And there was a wave of papers about this last spring, I think we can call it. So one of them was our paper where we looked at so radiation waveform. We ended up giving it in QCD and only parts of it in gravity. But then there are these other two papers. What was this one? So these people and these people, which at least Stefano's here.
So Graham and Josh.
Oh, sorry. Yeah. Okay. Everyone's here. I apologize. So everyone's here. Everyone knows what I'm talking about. And these people, if I'm not mistaken, gave the wave function for gravity. And then there was also this paper with Alessandro's not here, Carlo, who is here, and myself, where we gave the essentially the classical integrated 5.1 loop amplitude. Right, so I'll be looking at this radiation at one loop because as you know, these experiments keep getting better, the signal to noise ratio is going to get more and more complicated. So it's important to get these higher order corrections to this radiation. Now I'll be splitting my talk into roughly 3 parts. First, I'm going to set up this waveform observable from these expressions and see where we can plug in our scattering amplitudes. And to do this, we use the KMOC, or the Kassa or maybe O'Connell formalism, where we see that we can express them in terms of scattering amplitudes. And since that's one of the important ingredients, I'll also talk a little bit about how we find this amplitude or amplitude integrand, really, and how we can find it in gauge theory in a way that we can double copy it to also get the gravity results. And then finally, if I have time, we'll take a look at a few of the bits that we get for the QCD result of the actual waveform, the parts of the waveform that we care about. All right, so let's start setting up the waveform. The radiation waveform is associated with the expectation value of the field strength in gauge theory and the Riemann tensor in gravity. So the thing that we're going to be interested in here is the expectation value of this field strength. And I'm using the field strength here because it's easier to show, but it's essentially the same thing if you want to do it for the Riemann tensor. And 2 of the kind of starting ingredients that we need to set up this with the KMOC formalism is a parameter that we can use to control the classical limit. So something that we can expand in and point to say, here's our classical term. And also a well-defined initial state so that we can set up these expectation values. All right, so the parameter that we use is h bar. We kind of just reintroduce it into the expressions that we have by taking, so any momentum that we have of massless particles or messenger particles or loop momentum, all these get this h bar back, and then they're written in terms of their wave number. And also the couplings also get these factors of h bar. So we just plug that back in. And the other ingredient that we need here is this initial state. So I've borrowed this nice and simple form of our initial state from Donald's talk. So we've got, okay, this is a sketch of how we want to model this. We have our two point particles that are going to be spinless massive particles that are going to scatter past each other with an impact parameter b, and then we'll have some radiation coming off it. So the initial state gets, some integral, some Fourier integral, and then each particle is described by these wave packets that are peaked. So any uncertainty in the momentum or the position is kind of negligible for the classical expressions that we're looking at. Yeah, and I think that's probably what we need to know about the initial state here. So then we set up our observable, and I have another little sketch here. Right. So we don't want the sort of full observable over all time. We want kind of a momentum picture of this waveform. So we're just going to set up the observable here in terms of the out states. And now that we have our in states, we can get the out states by using the time evolution operator on the in states. And what does that look like? Well, that looks like the S matrix. So already here we see that we're going to have some amplitudes running around in here. So we plug in the observable that we care about, is the F here. And I think that's probably what I wanted to say here. So here we have sort of our expression so far for what we want to find. So our waveform, just scream out if I'm okay, so here we have our waveform. We see that we have this integral, there's some k's, there's some polarization vectors. I don't want us to care too much about that. And then we have here the expectation value in terms of these s's. And you see that I've gotten rid of my f and written it just in terms of this a, so the annihilation operator. You can sit down and write it yourself. You see that a lot of these other terms just go away because you start to annihilate things that don't have any gluons or gravitons. And sort of, well, I don't want to say before, but the way that you're probably used to seeing this expression, if you've seen it, is that we can use the unitarity of the S matrix and rewrite this so that we have these integrals and everything, and then we'd have the amplitude minus some cut of the amplitude. And that is indeed kind of how we started to set this calculation up. Oh, and yeah, this is, so in our case, this is the one loop amplitude, if that wasn't clear. But we decided to rearrange this expression into what we're at least defining as a real part and an imaginary part. And I've kept the amplitude and the cut here because we find that the main contributions that we care about to the real part are actually essentially one particle cuts of the one loop amplitude. And the parts that we care about in the imaginary part are going to be two particle cuts. And what we're also going to see is that this way of rewriting the expression makes it trivial to get rid of these superclassical terms. And by superclassical terms, I mean, you plug this h bar back in, and then you expand. And all of a sudden, you get these terms that have too many powers of h bar in the denominator. So we call these superclassical, and in fact, super duper classical for the over superclassical terms. But if you write it like this, they kind of trivially disappear. And what we also found is that this is a split up that makes more sense sort of physically, because when we look at these parts, the real part seems to be responsible for kind of the conservative forces. So if you can imagine, you have the two particles, and those are the forces where one particle radiates because it's moving in the force of the other particle. While the imaginary part is more related to, I don't know, dissipative or self force, whatever you want to call it. So the fact that we get radiation because the particle is moving in its own field. Right, I think that's what I wanted to say here. But as you can see, the amplitude and the cuts are still pretty important ingredients here. So in this next part, I want to give a very brief summary on how we actually set up this one loop amplitude. So this one loop amplitude was found by JJ and me many moons ago using a bootstrapping method where we essentially use two concepts to just bootstrap both tree level and one loop amplitudes. And these are the color kinematics duality and unitarity cuts. So let me, I'm sure you're all very familiar with the color kinematics in the double copy, but I'll give a lightning review just to refresh your memory. So what do we mean by color kinematics duality? I think the simplest thing to do is to look at just some 4-point gluon graph, essentially. Now, this graph, of course, when we dress it with what we want, gets a color factor. And in this case, this color factor consists of these two Fs. And it turns out that there's this relationship between the color factors that we call a Jacobi relation. And this Jacobi relation you can show in terms of the graphs like this. So color kinematics duality means that while here you have this nice relationship for the color factors, you also get some kinematic expression per graph. You have, the propagators in the denominator, and then you have some kinematic numerator. So what we want is that we want these kinematic numerators to obey the same Jacobi relations as the color factors. Yeah, I won't go into why you can do that, but you can do that. And here I'm just showing you a 4-gluon example. It's fairly simple, but you can do this for amplitudes where you also have massive particles. So the red line here is just some massive scalar. And this is essentially just rewriting the commutation relation of the color factors of these graphs. And in some cases, if you treat your massive states carefully, you can even have these relationships between 4 massive state amplitudes. This is also not just true for these simple 4-point amplitudes. It should be true for any kind of subgraph of a larger graph. So let's say we have some n-point L-loop amplitude. If you look at one of the internal edges, so this one, you should be able to change the connectivity of this internal edge. So if you imagine that it looks like an S channel, you turn it into a U channel and a T channel, and then the 3 resulting graphs should have the same relationship between their kinematic numerators. And then, right, so now you have a bunch of relationship between the different numerators of all these graphs in your problem. What you can do then is that you can reduce the number of independent numerators. You can write all your numerators in terms of these master numerators. So just to give you an example, these are some graphs that show up in our 5.1 loop amplitude. If you look at this, the pentabox, as Donald calls it, and we take a look at this internal edge, for example, if you change the connectivity to an S and a U channel, depending on what you want to call it, now you see that you can express this guy as a linear combination of these guys. And then you can give a function to each of these separate topologies, and using these relationships, we can kind of determine what this kinematic information should be. So reducing the number of independent information is one great thing about using color kinematics for this, but it also gives us the double copy, which is probably what we're more interested in this room. So if we take our graphs and we give them, a color factor, one of these kinematic numerators, and a propagator, as long as we made sure that that we're happy with all of these Jacobi relations, we can get rid of the color factor and replace it by another kinematic numerator, and this is going to give you a gravity expression for it. So in our case, where we have these massive scalars coupled to Yang-Mills, this is going to give us Einstein gravity, which is not completely true because, as you mentioned earlier, we also get these extra states. You have these dilitons and other things that somehow you have to go in and remove. But I think it's still easier than going the other way of getting gravity directly. Okay, so that was the kind of color kinematics part of this bootstrapping. And the other ingredient is essentially these unitarity cuts. And what that means is that we want our amplitude to factorize into these lower point amplitudes when we set propagators on shell. So here you see the 5 2-point cuts that you need to find this amplitude. And we take these internal propagators and we put them on shell. And we make sure that they factorize into these tree level amplitudes. Yeah, I don't know if there's very much more to say here, but okay. So now I realize that was very quick, but now we have, yes?
I can ask, so I remember that when one does this color kinematics duality at one loop, one has to add somehow terms that vanish upon integrations, like tadpoles and corrections to the external legs. Do you consider them, or you already think that because they are quantum, you can drop them at the beginning?
So that's a good question. Okay, I think there's 2 answers here. So when we set up this integrand, the idea was essentially just to see if we could have color kinematics at one loop with the massive particles. So we set up the full quantum thing. It's actually, it's generated, I mean, we found it using this automated code where I kind of, I stopped the code from generating more whenever I had something which I called a snail, which is like a bubble on an external graph. If I'd let it continue, would have found tadpoles. But that didn't, since kind of the motivation was also to find a classical result at some point, we didn't generate the tadpoles. I have some expressions for the snails, but they're not integrated and they have a lot of free parameters in them. Because we found all the numerators that we cared about, all the graphs that we cared about. And then when you plug it into the classical stuff, you're not really going to care about these tadpoles and snails. So
Classical computation, actually, you do care about the snails. That's what we found in the computation.
I'm not sure if what we call snails.
Yeah, there are different snails.
Oh, they are different.
which snails? I mean, okay. I mean this.
Yeah.
No, wait, this is 2 loops.
No, then,
not a snail.
yeah.
What animal is it?
Look like a
Kind of looks
snail.
like it.
Bubble on external leg.
Yeah.
That's gotta be a better name though. Zit? I don't know.
Wave function correction.
Sorry,
Wave function correction.
wave function correction? Okay. These guys. Yes,
I have well, okay, I don't want to take you too far away, but
no, go ahead.
I'm curious about the dilettante axion pollution when you do the double copy. I mean, are you avoiding that by virtue of working on the cuts here? Or what's the
No. No. So the cuts that I'm showing here are the gauge theory cuts.
yeah.
And I'm using d-dimensional state sewing. So I'm not controlling what's crossing the cut here. And essentially what we did is that we fixed on the gauge cuts because they're easier to do.
Yeah.
And then we double copied what we got, right?
You double copy at the level of the full integrands.
It was graph by graph.
Graph by graph, yeah.
Yeah. But then, so, okay, I'm actually glad you asked this. So then what we did is that now we had, shit ton of graphs in gravity with all sorts of things running around. Well, actually, they're mostly dilettantes, right? Because you have the massive scalar states. So what we did was that we used this kind of method of maximal cuts, where for each graph, we went in and cut every internal propagator with these graviton projectors. And then, whenever we got something that wasn't a graviton, we just subtracted that from the numerator.
Okay, so it's
Then you do the next to maximal and the next to maximal until you have a set of graphs where you've gone in and manually removed.
I see. So you started off with the axion delta and then you systematically removed it.
Yes.
Okay, cool.
And but what Henrik and I are working on now is trying to find a way to double copy directly to the dilettante terms. Or okay, I'm calling it the dilettantes because here it's mostly dilettantes, but the non-graviton terms. so that instead of going in and having to do all the cuts for everything, you could just take these numerators, double copy them graph by graph, and then take this square root of dilaton graphs and then square that and subtract it, and then you'd have the pure gravity result. Did that answer your question?
Definitely.
I'd gotten here, I think. How am I for time? Left or gone? Okay.
One thing in attention to my. Hold on.
Okay, so now we have the ingredient. We have the gravity ingredient, but we also have the QCD ingredient. So let's take a quick look at how we plug this back in. And I apologize, I realize this looks a little bit messy, but it's also to give you the sense that, you know, this is a lot of graphs and expressions that we're talking about. And in fact, if you write down all the graphs, there are 116. And for those of you who care, there are 33 different topologies. And then, you know, the graphs are different relabelings of these. Of course, we don't care about all the 116 graphs, but it's a large integrand to start with. But luckily in QCD, you can kind of rearrange a little bit, and you have these color factors that you can gather on. So you can rewrite this in terms of just 16 independent color factors with partial amplitudes that are, of course, smaller and easier to handle. And let me just see if I remember this correctly. Yes, okay. So now you can at least, in QCD, you can at least take each partial amplitude and calculate it on its own. And what we found, which is of course not very surprising, is that some of these partial amplitudes are in fact the QED contributions. So let's just take a bit of a closer look at this A3, this partial amplitude that I'm showing you here. And this is kind of just a side note. So these are the graphs that contribute to this partial amplitude that I showed you. You know, look at, I don't know how easy it is to see, but they're all either pentagons or, does anyone have a preferred name for this? Boxes, dangly leg boxes? No complaints.
It's a box.
It's a box. Well, it's a dangly box. Okay, boxes and pentagon.
Held box.
Hmm?
Held box.
Okay, there we go. So all of these are the graphs that contribute, because their color factors can be written in terms of this color factor that I showed, and that is this color factor. So in this one, I mean, so this is the same graph, so it's not so surprising. But for this guy, for example, oh, sorry, I keep pointing with my fingers and with the thing. So with this one, we had to kind of expand these color factors into the basis that we chose. And a kind of interesting thing here is, because of the way that you write color factors and their commutators when you write them classically in terms of KMOC, and I'm sorry I didn't put a citation here, but there's a very nice paper on QCD, classical QCD, also by people from here, where you get these H bars when you have the commutator relation between the keys. So for the color factor of this guy, you actually see that this would be kind of the leading contribution, the color factor that we're looking at here. And all the others get these extra powers of H bars. So they're actually kind of suppressed in the classical expression. All right. So this is just a quick technical detail. Here's the expression in terms of the graphs. And as I mentioned, you can kind of see that this is also the QED expression. And if we take each of the graphs, we can see how we put the H bars back into the kinematics here. So you see that you get these H bars back where you have loop momentum and where you have these massless external states and the messenger momentum. All right, so here's some actual results. And what we're looking at here is the real part, or we've been discussing what we're going to call it, but I'm calling it now the real part, or kind of the conservative contribution to this waveform. And you see that we get, essentially we've split it into two terms. One term where this is the heavy mass term, which contributes when this mass is heavy. And yeah, so you see that we get this delta function on the particle that we're cutting. So as you might remember, the real part gets contributions from these one particle cuts. And then here's the expression if you're interested, but they're not horribly complicated. Yeah, and in fact, these are the QED results, as you can see maybe here from the charges in the factory here. And this is the other contribution, which is where the masses are more, where they're more equal mass. And yeah, essentially this is the expression. And then there's also the imaginary part. I'm not going to show the entire imaginary part. This is just to show you an example of one of the graphs that go into this. And as you can kind of see, this is a typical like cell force radiation reaction graph where you've got this particle running around and it kind of gets this loop that makes itself radiate again. And here we have to cut these two particles. So we see that we get these kind of sewing together Compton amplitudes out of this. I'm not gonna.
You might want to speed up a bit.
Oh, okay. Yeah, I'm actually almost done.
5 minutes.
Oh, okay. I have a bunch of time then.
Okay.
So, okay. So what I showed you now was we set up kind of the QCD waveform. The example, the partial amplitude that I showed you was kind of secretly a QED amplitude. But we can find the full QCD waveform by calculating the other partial amplitudes. And of course, we don't care about all of them. We don't care about these guys, and but it's not so complicated to set up the rest of the calculation. And then for gravity, we already have these graphs that we can double copy to get the gravity results, and we've also removed the dilitons. So you can essentially do the same thing with the gravity amplitude, and that should give you the gravitational waveform. Okay, so I'm actually just going to sum up. So we can calculate these radiation waveforms using this KMOC setup, and we can calculate it for QED or QCD or gravity. And we actually split it into this real part and imaginary part that have different physical meanings. So they express the, let's call it the conservative part and the radiation reaction part of the waveform. And the input into these are these one loop amplitudes and cuts that we can find using a bootstrapping amplitude where we get both kind of QCD and gravity results for free. Oh, I think maybe that's what I wanted to say there. So what now? I'm going to make this very quick because I think Stefano has better kind of what now questions at this point than I do. But I think what we're mostly interested in now is understanding better this kind of split into the imaginary and the real part, understanding the physics behind it. It would, of course, be nice to go to higher loops, to two loop. But then the question is, you know, how much work is it to find the two loop result? And then how interesting will it actually be? Although we found a surprising amount of interesting physics at one loop, so who knows? And then how can we relate this to the bound states, which I think Ricardo also gave us. There you go. I leave that to you. Yeah, I think that's actually what I wanted to say.